Hello, everybody. Welcome to AP Calculus AB. So here we are in Lesson 1, Finding Limits Graphically and Analytically. So I'm hosting this because I wanted to help people who want to get a head start in calculus, who are like going into the class, or someone who needs review help. So that is the purpose of hosting this. So we have some learning targets we need to hit. So we want to estimate a limit using a numerical or graphical approach. We also want to learn the different ways that a limit can fail to exist. And then we want to use the formal definition of a limit and study that and know what that means. So without further ado, let's jump right into the definitions. So these are some terms you're going to need to know for this lesson and just calculus in general. A function value. So this is finding the location of the y value of the graph at a specific x value. So in this case, our x value that we're looking for is right here. This is 2. Let me switch to red just so it looks a bit better. 2 is right here. And so we're trying to find the specific y value of the graph at this point. So the notation we would write this in is, let me write the word notation. I'm doing this on mouse, so it's not going to look super pretty. So the notation we write this in is going to be f of 2. So this is what this would look like. F of 2 is what we're looking for. And in this case, this point would not exist because this is a hole. So this one is solid for a reason. This one is a hole. We are looking for whole y values, or y values that are solid in their shading, not holes. But if this was a solid shape, like this, for example, so if this was solid, we would say this would be 4. But since it's not going to equal anything right now. There would be no point. So then the next one is a limit value. So this is the y value that a function or graph approaches as the x value moves closer to a given constant. So this one, when it says moves as the x value moves closer, this is talking about both the left and the right side of the equation. So right here at this point, it is asking for, we're moving closer on the left side right here, as that indicated by these arrows, and the right side. So if these are the same, if they converge on the same point, then we have our answer. So if we're trying to find the limit of, actually let me rewrite this so it's in its better notation. Limit of f of x as x approaches 2, because this is our x value down here, because again, x value, this would be 4. Now, holes don't matter on here because it's still one single point that it's converging on, so this doesn't matter. It's only when we're doing specific points with function values right here that the holes matter, but it doesn't matter with limit values because they're still converging on the same point here. So the limit as f of x is approaching 2 is 4, because this is the y value associated with this point. It's not drawn perfectly, but just imagine this is drawn perfectly to match with this point. So yeah, that's what those mean. So this is the next part of our lesson. This is where the limits do not exist, or we just write it as DNE. This is just a quick abbreviation. So example 1, this is the graph of the absolute value of x over x. So right here, like I said on the previous slide, we are trying to find in this one we're trying to find the limit of f of x as x approaches 0, which would be right here, that's x of 0. But in this case, it does not exist because this is 2 different lines. So we go from here, we hit 0, and then we jump, which is why this is called a jump discontinuity. We jump to a different line. We don't get a specific value out of this, so this would not exist, because the point of this is to find the value where these 2 lines from the left and the right side converge to give us our limit value. But since these are 2 different lines and the lines jump to another one, this doesn't exist. So that's why that is D and E. Our next example is f of x is equal to 1 over x squared, as beautifully drawn, as you can see. It's perfect. This is a vertical asymptote, so limits don't exist at vertical asymptotes, which you should know if you took precalculus is just like basically what I like to call a barrier that prevents these two lines from converging on a single point ever. So they're going to get infinitely closer, ever so slightly closer, but they will never touch because of this vertical asymptote. He will never let them touch. Nothing. So, because of that, this does not exist, as it's trying to approach 0 since the vertical asymptote is at x of 0, and we cannot, the asymptote is preventing us from finding a value for this. So, again, D and E. Our last one is oscillating behavior. This is the graph of f of x is equal to sine of 1 of x. I definitely did not draw this as well as I could have, but basically this is a bunch, so it goes in, goes up, hits 1, that's 1 right here, and then goes up and down very, like, repeatedly. It's not supposed to be, like, one solid line, or, like, mismantled mesh like that, but that's kind of just how it ended up being drawn. But it's basically going up and down repeatedly, and then it finally ends and then goes out. Obviously, since we're trying to find at 0, there is not one single point that this converges at all, because it's just a huge amalgamation of lines closely put together. I mean, it's oscillating, and then it leaves, and then it continues out past 0. So that does not exist. We cannot get a single point where these converge at. So these are the examples where limits don't exist, right there. Again, just a quick review. Jump discontinuities. One line, we're trying to find it at a specific point. One line jumps to another, like this. A vertical asymptote, which basically just prevents these two lines from ever touching. And then oscillating behavior, where there's just a bunch, it's a huge mess right in the middle, and we are never going to get one specific point out of that. Okay, now here is our big practice problem. So here's our graph. It's not the greatest quality, but it's a graph nonetheless. So we are asked to find the limit of f of x as x approaches -8. So here is -8 on the x-axis right here, and we're trying to find the y value as from the left side and the right side. So -8 happens to exist it's right there, and it is at 1. That is where both this line and -8 happen to correspond. So the answer would be 1 for this, because again, as it's going from the right side, it hits 1, and as it goes from the left side, it hits 1. Okay, the next one. The limit of f of x as x approaches -7. -7 is right here where this hole is, but this one actually just does not exist, because again, this is our jump discontinuity rule, because we're trying to find where it goes on the left side. So on the left side, it's right here at 0, but on the right side, it's down here at -4. So that doesn't exist. It goes from one line, starts at another. That's a jump discontinuity, so it does not exist, or D and E as our answer. Okay, f of -3. So here is -3 on our x-axis right here. And then if we look down, it's a little hard to see the line. It's very thin, but right here, this solid line right here, remember, we don't want holes. Holes those aren't like solid points. We want a solid straight point that gives us our answer, and so this straight point on the y that corresponds to the y-axis is at -3. So f of -3 equals -3. Okay, the limit of f of x as x approaches 4. So here is 4 on our x-axis right here. And again, this guy right here would be at -1. Because on the left side, here we go. Boom, boom. It's supposed to be a good arrow. Pretend it is. And right here, on the right side, it converges right at -1. Let me draw a straight line just so it's a little bit easier to see. Right there at -1. Bam. Right there. So that is -1. The limit of f of x, x approaches 4, would be -1. All right, next one. F of 4. Now this is at the same point right here. Let me... Oh, I don't want to erase the graph. Whatever. We'll keep this here. F of 4 here is 4 on our x-axis, and again, we don't like holes, like I mentioned earlier. So right here is our hole at 1, and so our answer for f of 4 would be 1. All right, the next one, f of 6, right here. So since there is no, since we don't like holes for like the same as the last one, but there's no solid point on this one. So that would mean it's undefined. I'm just gonna say, oh, that's a bad E and a bad D. It's still very spaced away. Sorry, I'm writing on mouse, so on def. There, that's how we like to abbreviate it sometimes. So that's undefined because there's no solid point for this to equate to, and since we don't like holes, like this one is, that it just doesn't, it's undefined. There is no proper value for this to exist at, so the f of 6 is undefined. Next one, the limit of f of x as x approaches 6, right here. Now this one we don't care if this is a hole, so on the left side, right here, and the right side, it approaches at the point, oh, I guess I blocked 6 out. There. I'll write it there. Okay, these converge at the point 1. So, at the left side and the right side, again, we don't care about holes for when we're doing limit stuff. So, this would be 1. That's where they converge at. Okay. And then our final one for this practice problem is the limit of f of x as x approaches 7. So 7 is right here, but this one does not exist, just like the one for -7 right here. That is not a very good arrow at all. There we go. Like this one is a jump discontinuity because there's 2 separate lines. So on the left side, it goes at -2, but then it's all the way up at 7. That is, we don't have a specific point, so it just doesn't exist. D, N, E. So there we go. That is lesson 1. That is lesson 1 of finding limits graphically and analytically. I hope you guys enjoyed, and tell me what I can improve on, because this is my first time ever trying to do teaching a math kind of deal like this. And yeah, like and comment down below.